In this lesson, we will now look in greater detail at some of the other components that make up an aircraft's hydraulic system. The first component we are going to discuss is the reservoir. You may think that in a sealed leak-free system, a reservoir would not be necessary. However, that is not true. Firstly, no system can ever be leak-free. In fact, we have already said that a very small amount of fluid is allowed to leak across the seals of actuators in order to lubricate them. Also, the fluid expands and contracts as it is heated and cooled. And as we shall see later, some types of hydraulic actuator need more fluid when they are extended than when contracted. The extra fluid is stored in the reservoir when not required. Most hydraulic systems also have accumulators fitted, and these will contain variable amounts of fluid depending on the system configuration. Again, we will discuss these in greater detail shortly. When a hydraulic pump is operating, as well as supplying pressure at its outlet, it also, of course, sucks fluid in at its inlet. This suction causes a big drop in the pressure of the fluid and can lead to low temperature boiling and the formation of bubbles. When these bubbles pass through to the pressure side of the pump, they then implode with great force. This is known as cavitation, and if allowed to happen, it can cause severe damage to the pump. The sound of pumps operating while cavitating can range from a low-pitched steady knocking sound, like on a door, to a high-pitched and random crackling, similar to a metallic impact. The reservoir helps to prevent cavitation by providing a head of fluid for the pump. To do this, the reservoir is located higher in the system than the pump to produce a positive pressure at the pump inlet. In many installations, the reservoir is also pressurized with air from the engine compressor to further increase the fluid pressure at the pump inlet, thus reducing the possibility of cavitation at high altitude. Another way that reservoirs are pressurized is by the bootstrap method. A piston sits on top of the fluid in the reservoir. It is pushed down by an actuator powered from its own hydraulic system, pressurizing the fluid. When the system is not operating, the pressure is held by the non-return valve. The reservoir also contains connections for suction pipes to the pumps and return pipes from the system. A quantity transmitter unit to allow the flight crew to monitor the system for correct servicing and in-flight leaks. A filling inlet, normally sealed with a filler cap. Note the strainer in the filler inlet, preventing debris entering the reservoir. And, in some cases, a temperature sensing probe, which may be used to operate a fluid temperature gauge and/or an over-temperature warning light. The baffles and fins are fitted to prevent sloshing and foaming of the fluid during in-flight maneuvering. In systems which are fitted with more than one pump, usually the main pump is engine-driven, whilst the backup may be electrically or pneumatically driven, or may even be a hand pump. The main pump will draw its fluid through a stack pipe in the reservoir, whilst the backup will collect its fluid from the bottom of the reservoir. This ensures that if fluid is lost from that part of the system supplying the main pump, or supplied solely by the main pump, a reserve of fluid for the backup pump will still be available. It is very important that hydraulic fluid is kept free of foreign bodies, Any debris would quickly damage the pump and components. It would also cause problems in things such as pressure relief valves, as they can have very narrow passages which are easily blocked by foreign particles. Filters are fitted in both suction and pressure lines, that is, on both sides of the pump. The suction filter protects the pump, and the pressure filter ensures the cleanliness of the hydraulic fluid during use. There is also sometimes a filter fitted in the fluid return line to the reservoir to remove particles picked up during component operation. Filters remove foreign particles from the fluid, thus protecting the seals and working surfaces of the components. Some filters are fitted with a device which senses the pressure differential across the filter element and releases a visual indicator in the form of a button or illuminates a warning lamp when the pressure differential increases as a result of the filter becoming clogged. False indication of element clogging as a result of high fluid viscosity at low temperature is prevented by a bimetal spring, which inhibits indicator button movement at low temperatures. Other filters are fitted with a relief or bypass valve, which allows unfiltered fluid to pass to the system when the element becomes clogged. In this type of filter, the element must be changed at regular intervals before clogging occurs. Some filters combine both systems, with the warning indicator set to operate shortly before the bypass valve opens. Individual components often have a small filter fitted to their inlet connection, and constant pressure pumps will have a case drain filter to help monitor pump condition. We will cover the term case drain when discussing pumps. Filter elements may be manufactured from paper, felt or gauze, from metal wire, or from a combination of these materials. All elements, except those made from wire, are usually discarded when removed, but wire elements may usually be cleaned. Cleaning by an ultrasonic process is normally recommended, but if a new or cleaned element is not available when the filter becomes due for check, the old wire element may be cleaned in a suitable solvent as a temporary measure. An accumulator is a device used to store hydraulic fluid under pressure. Two different types of accumulator are illustrated here, but many other types are used. However, the two shown are those most commonly in use in aircraft systems. Whatever its shape, the chamber of the accumulator is split into two parts by a separator. In the case of the cylinder, a floating piston is used, whilst the spherical accumulator has a flexible diaphragm. For the purpose of this explanation, we will concentrate on the cylindrical type, as this is the most common of all. The volume on one side of the floating piston is pressurized with air or nitrogen, and the other is connected to the hydraulic system pressure line. The gas side of an accumulator is normally inflated through a charging valve, which may be attached directly to the accumulator or installed on a remote ground surfacing panel and connected to the accumulator by means of a pipeline. The charging valve usually takes the form of a non-return valve, which may be opened by means of a plunger in order to relieve excessive pressure. To pre-charge or check the gas pressure, the system hydraulic pressure should be released. This will allow the gas pressure to move the floating piston to the bottom of the accumulator. When a pump is operating and hydraulic pressure builds up in the system, the gas is compressed until fluid and gas pressure equalize at normal system pressure. At this point, the pump commences to idle, and system pressure is maintained by the accumulator. The accumulator gas pressure gauge will now read system pressure. A non-return valve is fitted upstream of an accumulator in order to prevent fluid from the accumulator being discharged back through the pump to the reservoir. The accumulator carries out a number of functions in the system. It helps to dampen out pressure fluctuations. It allows for thermal expansion and contraction of fluid trapped in the pipes. It can provide a small emergency supply of fluid to the system in the event of pump failure. The initial gas charge of the accumulator is greater than the pressure required to operate any service, and the fluid volume is usually sufficiently large to operate any service once, except that brake accumulators normally permit a guaranteed number of brake applications, or the ability to stop the aircraft during a rejected takeoff. If the system is using a constant delivery fixed volume type pump with an automatic cutout valve, it will prolong the period between cut-out and cut-in of the automatic cutout valve, and so reduce the wear on the pump. Operation of the automatic cutout valve will be explained shortly. The accumulator will also provide the initial fluid when a selection is made and the pump is cut out, or at minimum stroke. If a service is selected, a supply of fluid under pressure is available until pressure drops sufficiently to bring the pump online. Incorrect pre-charge pressure of the main accumulator can cause the automatic cutout valve to cut in and out too frequently. This may cause rapid fluctuations of system pressure, which can be felt and heard as hammering in the system. This can rapidly cause damage to the system if it is not dealt with. An automatic cutout valve, ACOV, is fitted to a system employing a constant delivery fixed volume pump to control system pressure and to provide the pump with an idling circuit when no services have been selected. The ACOV consists of a piston, which is sensing system pressure. This is opposed by a spring. The piston is controlling a poppet valve. The ACOV operates in two modes. These are known as cut-in and cut-out. The valve is in the cut-in position when spring pressure is greater than pump output pressure. The piston is fully down and the poppet valve is closed. Cut-out is when hydraulic pressure is greater than spring pressure. The piston moves up and the poppet valve is open. This allows the pump output to return to the reservoir. With the system not operating and the pressure zero, the ACOV will be in the cut-in position. When the pump starts operating, pressure will build up until when normal system operating pressure is reached. The pressure on the bottom of the piston will overcome the spring. The piston will move up, opening the poppet valve and allowing the pump to return its fluid output to the reservoir without any load. There will still be fluid flowing through the pump to cool and lubricate it. This is the cut-out position. System pressure will be held on the bottom of the piston by the non-return valve. When a service is operated, system pressure will fall. The spring force will now be greater than the hydraulic pressure, so the piston will move down, closing the poppet valve. This will cut off the pump return to the reservoir and allow it to operate the service. The ACOV will remain in the cut-in position until the service reaches the end of its travel and pressure builds up again. It will then return to the cut-out position. This type of system needs a reservoir of fluid energy downstream of the automatic cut-out valve. Otherwise, any slight leakage through components or from the system would result in frequent operation of the valve and frequent loading and unloading of the pump. An accumulator fulfills this, as well as a number of other functions. The time between cut-out, offload, and cut-in, onload of the ACOV is a good indication of the condition of the system. External leakage will cause a reduction in the operating period, with frequent loading and unloading of the pump. Internal leakage, usually caused by a piston seal failure, will similarly cause frequent loading and unloading of the pump. This could also cause an increase in fluid temperature due to the extra work being done by the pump. That is the end of the lesson on components. To summarize the main points, a reservoir provides both storage space for the system fluid and sufficient air space to allow for any variations of fluid volume in the system, which may be caused by actuator ram displacement or by thermal expansion. It compensates for small leaks, and it provides a head of fluid for the pump. Most reservoirs are pressurized to provide a positive fluid pressure at the pump inlet in order to help prevent cavitation. Filters are used to protect pumps and other system components from damage caused by foreign particles in the fluid. An automatic cut-out valve is fitted to a system employing a constant delivery fixed volume pump to control system pressure and to provide the pump with an idling circuit when no services have been selected. Finally, an accumulator is fitted to store hydraulic fluid under pressure in order to dampen pressure fluctuations, to allow for thermal expansion, to provide an emergency supply of fluid to the system in the event of pump failure, and to prolong the period between cut-out and cut-in time of the ACOV, and so reduce the wear on the pump. It also provides the initial fluid when a selection is made and the pump is cut out.